Welcome back to The Explainer. Today, we're tackling something that's honestly one of the most frustrating traps in all of data science. You know the drill. You're building a model, and in this desperate quest for perfect accuracy, you just start throwing every single piece of data you have at it. More columns, more variables, the whole shebang. But instead of getting smarter, your model just trains painfully slowly, it overfits like crazy, and suddenly its predictions are a total mystery. Well, today, we're going to fix that. We are making a critical shift from just wanting more data to wanting the right data. And our ultimate tool for this? Feature selection.
Okay, let's dive right into this. Look at this quote because it absolutely shatters a massive misconception. More features is not better. The right features is better. When you're first learning data science, it is so incredibly tempting to think that just adding more features will automatically make a model smarter. It kind of feels like giving a student more books to read so they'll get better test scores, right? But as you'll see today, feeding a model useless, redundant, or just noisy information doesn't make it smarter. It actively confuses it.
Here's our roadmap for today. We'll start with recursive dimensionality, then move through filter methods, wrapper methods, and embedded methods, before finally wrapping up by comparing them all.
Let's start with Section 1, the curse of dimensionality.
So let's introduce the main villain of our data science story. Imagine you've got a data set with, say, 500 features. You might think, awesome, I'm rich in data. But actually, you're probably suffering from the curse of dimensionality. See, as the number of features or dimensions grows, the sheer volume of your feature space just explodes exponentially. It's literally like trying to find your keys in a tiny studio apartment versus looking for them in a massive empty warehouse. Suddenly, your data points that seemed all packed together in a 2D or 3D space are incredibly sparse. The distances between points start to converge, meaning everything looks equally far apart. And when that happens, your model needs an exponentially massive amount of data just to find real patterns. Worse yet, all those noise features just completely drown out the actual signal. Overfitting isn't just a risk anymore, it basically becomes the default state, making your model totally impossible to explain.
So the crucial point here is that feature selection is the absolute antidote to this curse. By stripping away the noise, we force the model to focus only on what actually matters. And basically, all feature selection techniques fall into one of three distinct families. You've got filter methods, which score features independently and are blazing fast. Then there are wrapper methods, which actually train a model to test feature subsets. Super accurate, but really expensive computationally. And finally, embedded methods, which do the selecting right in the middle of the training process itself. Let's break each of these down.
Moving into Section 2, filter methods or fast scoring.
Think of filter methods as the frontline bouncers at the door of your dataset. They are incredibly fast, mostly because they evaluate each feature totally in isolation, no model training required. The simplest one to grasp is the variance threshold. Look at the logic on the screen. If a feature in your dataset has a value of 0.04 for, let's say, 999 out of 1,000 samples, its variance is near absolute zero. It's pure noise. I mean, no machine learning model in the world can use that feature to distinguish between classes. So we just set a low threshold and boom, we instantly drop every feature that falls below it. It is just a fantastic, low-effort first step to catch obviously useless features at almost zero computational cost.
But what about features that actually do vary? Well, a lot of people jump straight to calculating correlation. But simple correlation has a big flaw. It only looks for linear relationships. If your feature has a U-shape or maybe a quadratic or periodic relationship with your target, correlation is going to totally miss it and just score it a zero. And that is exactly why mutual information is so powerful. It measures how much knowing the value of feature X reduces our uncertainty about target Y. It completely bypasses that linear limitation and really uncovers those hidden complex dependencies in your data. It's a real game changer.
All right, Section 3, wrapper methods or iterative pruning.
Now, filter methods are great, but they have a pretty massive blind spot. They completely miss how features interact with each other. To fix that, we bring in wrapper methods. These actually use a model's own performance to evaluate subsets of features. The most famous one is Recursive Feature Elimination, or RFE. Check out this iterative loop. You start by training the model with every single feature. Then, you rank them by importance, maybe by looking at the coefficients if it's a linear model. Next, you chop off the absolute least important feature. And here is the magic step. You don't just keep chopping based on that very first ranking. No, you repeat the entire process. You train again. Why? Well, because removing one feature actively changes the importance of all the remaining ones. Features interact. So this iterative pruning ends up being incredibly thorough.
However, that thoroughness comes with a pretty staggering cost. Look at this number, 490. If you start with 500 features and your goal is to whittle that down to exactly 10 using standard RFE, you have to completely retrain your model 490 separate times.
Seriously, if you're using a complex algorithm on a massive dataset, you might as well go on vacation while you wait for that to run. It is a highly, highly expensive approach.
Let's look at Section 4, Embedded Methods, which are all about built-in pruning.
So what if we could get the model to do the pruning automatically while it trains, without the crazy endless looping of a wrapper method? Enter embedded methods. Take L1 or lasso regularization. And this brilliantly illustrates how embedded methods work by actually altering the math of the model itself. By adding the absolute value of the weights to the loss function, L1 creates this strict, diamond-shaped constraint region. The mathematical optimization naturally pushes the weights of the less important features right into the sharp corners of that diamond, forcing them to equal exactly 0. It acts like a penalty that literally kills off features. Now compare that to L2, or ridge regularization, which uses a circular constraint. L2 will shrink feature weights, making them super small, but it rarely forces them all the way to 0. So L1 actively selects features for you during a single training run.
Another massive embedded method comes from decision trees, like your classic random forests. Trees naturally rank features by how much they reduce impurity with every single split. But a quick warning here, tree importance has a major flaw. It's heavily biased toward features with high cardinality, meaning features with a ton of unique values, like an ID column. To fix this, we use something called permutation importance. The philosophy here is brilliantly simple. Shuffle and measure the damage. You literally take a fully trained model, shuffle the values of one specific feature, and see how much your accuracy drops. If performance collapses, well, that feature was critical. If nothing changes, the feature was useless. It perfectly avoids that cardinality bias, although, just a heads up, it is quite a bit slower to run.
Let's move to Section 5 and see how this all builds together, comparing and choosing methods.
Let's bring it all together for our grand synthesis. Now, what's really interesting about this slide is the ultimate comparative matrix we have here. You can clearly see the trade-offs. The filters, like variance threshold and mutual information, they're incredibly fast but totally blind to feature interactions. On the other end of the spectrum, permutation importance and RFE capture those intricate interactions beautifully, but man, they are incredibly slow to process. And then your embedded methods, like L1 and tree importance, they sit right there in the middle, offering a really solid balance of speed and integration.
So, after all that, what's actually the best approach? Well, the secret is you don't just pick one, you build a pipeline. Look at how these methods chain together perfectly, almost like a funnel. Step 1, you use the ultra-fast variance threshold to instantly catch and drop all those flatlined zero-variance features. Just get rid of them. Step 2, you use mutual information to filter down to the top 50%. This ensures you keep those complex, nonlinear relationships while cleanly cutting your dataset in half. And Step 3, now that your dataset is way more manageable, you can safely unleash the heavy artillery. You run recursive feature elimination on the survivors to thoroughly prune out redundancies based on actual model interactions. By doing this, you get the blazing speed of filters right alongside the deep accuracy of wrappers. Best of both worlds.
Which brings us to our final thought for this explainer. The true art of data science isn't about hoarding every possible data point. It is all about distillation. The goal is not to use all available information, but the right information. By mastering feature selection, you cure the curse of dimensionality, you slash your training times, and you build models that are actually robust and explainable. So, looking at all the tools we covered today, how are you going to build your next feature selection pipeline? Thanks for joining me on this explainer, and I'll catch you next time.